There is a single silicon chip, roughly the size of a fingernail, sitting inside a laboratory in California that some of the smartest people in the entire technology industry now believe could quietly determine which country actually controls the next 50 years of global economic and military power. That is not hyperbole. It is the sober, considered view of engineers, government officials, and corporate strategists who have spent years watching the United States and China race toward the exact same finish line in quantum computing, a race most people only ever hear about through the occasional flashy headline. This week, one specific piece of hardware pulled so far ahead in one crucial, unglamorous corner of that race that it is already reshaping corporate acquisitions, government funding priorities, and the broader strategic conversation about who actually wins the technology competition of this century. It is the kind of story that will likely never trend on social media in its own right. Buried under technical jargon, most casual observers would scroll straight past. And yet, it may genuinely matter more for the next several decades than almost any other single headline currently circulating about the broader technology race between these two countries. Stay with me, because by the end of this video, you will understand exactly why this single chip matters so much more than its tiny physical size would ever suggest. To understand why a chip could possibly carry this much strategic weight, you first need to understand what is actually at stake in the broader quantum computing race, because it is genuinely different from anything that came before it in the entire history of computing. A classical computer, the kind sitting in your pocket or on your desk, stores information as bits, each one simply a 0 or a 1. A quantum computer instead uses qubits, and thanks to strange quantum mechanical properties, a single qubit can effectively represent a combination of both 0 and 1 simultaneously. String enough qubits together, and in theory, you unlock a computational power capable of solving certain problems that would take a classical supercomputer longer than the current age of the universe to complete. Simulating complex molecules for new medicines, optimizing global logistics networks with millions of variables, and potentially even breaking encryption systems that currently protect global banking and government communications. All of these become theoretically possible with a sufficiently powerful quantum computer, and none of them are currently possible with even the fastest classical machines on Earth. It is worth understanding that quantum computing has no single dominant physical approach the way classical computing settled on ordinary silicon transistors decades ago. Different companies and research teams around the world are pursuing wildly different physical methods for actually building a qubit. Some use tiny loops of superconducting metal cooled to temperatures colder than deep space. Others trap individual charged atoms using precisely tuned lasers. Some use individual particles of light, called photons, threading them through optical circuits. Still others trap neutral atoms in delicate arrangements using laser tweezers, and a smaller but growing group builds qubits directly inside ordinary silicon, the exact same base material that has powered the entire semiconductor industry for the better part of a century. Each approach carries genuine advantages and genuine drawbacks in terms of stability, control complexity, and how easily it can eventually be manufactured at scale. And for years, nobody, not scientists, not investors, not governments, could say with full confidence which approach would ultimately win this race, which is part of why so many different countries and companies have continued placing parallel bets across currently protecting financial transactions, diplomatic communications, and military command systems relies on mathematical problems that are, for all practical purposes, impossible for classical computers to solve within any reasonable time frame. A sufficiently powerful, fault-tolerant quantum computer could theoretically solve those same problems dramatically faster, rendering some of today's most widely used encryption methods obsolete. Intelligence agencies on both sides of the Pacific have reportedly spent years quietly stockpiling encrypted data they cannot currently break, betting that a future quantum computer might eventually decrypt it retroactively, an approach security researchers often refer to as harvest now, decrypt later, whichever nation reaches that. Capability first gains not just scientific bragging rights, but a genuinely consequential and potentially durable intelligence and security advantage over any other government still relying on encryption methods a working quantum computer could eventually crack. For years, the biggest obstacle standing between today's fragile experimental quantum computers and tomorrow's genuinely useful machines has not actually been the qubits themselves. It has been something far less glamorous, the wiring, and an unglamorous engineering detail that rarely makes it into the more excited headlines surrounding this entire field. Every quantum computer you have ever seen a picture of the ones that look like glowing golden chandeliers hanging inside a metal tube, is actually a tiny quantum chip connected to a massive forest of wires and electronics sitting outside the freezer. Those qubits only work when cooled to temperatures colder than deep space, and every single one typically needs its own dedicated wire, running from room temperature control equipment all the way down into that frozen core. Scale that up. Toward the thousands or millions of qubits a truly powerful machine will eventually need, and you run headfirst into a physical wall. There is simply no way to fit that many individual wires into a refrigerator, and every wire that does fit carries a tiny bit of unwanted heat, straight toward the fragile quantum states you are trying to protect. Engineers have been calling this the wiring bottleneck for years, and solving it has quietly become one of the single biggest prerequisites for quantum computing ever scaling into something genuinely useful. This week, a research lab called HRL Laboratories, based in Malibu, California, published a paper in the prestigious scientific journal Nature describing a genuine breakthrough on exactly this problem. HRL is based on a research campus with a genuinely wild pedigree, the same site where engineers invented the self-aligned gate MOSFET, the tiny transistor structure that quietly became the foundation of almost every microchip made on the planet today, and the same site where the world's very first laser was built. For years, the lab was jointly owned by Boeing and General Motors, quietly working on foundational hardware, the unglamorous plumbing of quantum computing, while other companies around the world fought very public battles over who had the most qubits or the flashiest press release. HRL engineered a custom control chip that lives inside the refrigerator itself, right next to the qubits, operating at a mind-bending negative 450 degrees Fahrenheit, barely a few degrees above absolute zero. That chip generated every single control signal needed to run an 18-qubit device, built on top of an array of 54 quantum dots fabricated on two 100mm silicon germanium wafers, the same wafer size widely used across the commercial semiconductor industry, and executed quantum error correction. Essentially, the immune system that protects fragile quantum information from constant environmental noise completely on its own, with zero real-time input from any room temperature equipment, to physically connect that frozen control chip to the qubits without reintroducing the exact wiring nightmare. It was designed to escape HRL engineers. Developed a high-density ribbon cable made from superconducting niobium layered onto polyimide, carrying nearly 300 separate channels through a single flexible strip instead of hundreds of individual bulky wires, a small but critical piece of engineering that keeps unwanted heat from ever reaching the fragile quantum environment. Crucially, the entire system, the qubits, the control chip, and that specialized interconnect was built using standard complementary metal oxide semiconductor manufacturing techniques. The exact same basic process already used to mass-produce ordinary computer chips found in your phone or your laptop. That last detail is the single most important thing to understand about why this particular chip matters so much strategically. It is not just that HRL proved the underlying physics could work. Other research teams around the world, particularly strong academic groups across Europe, had already demonstrated pieces of this exact concept in laboratory settings years earlier, publishing regarded papers on cryogenic control electronics that the entire field still references today. What HRL proved is that a complete, self-contained, fully autonomous version of this system could be built using processes compatible with an ordinary commercial chip factory, the kind of factory that already exists by the thousands and already knows how to manufacture reliable products at massive scale. That is the difference between an impressive one-off scientific demonstration and something an entire nation could actually build a manufacturing industry around. If you're enjoying this kind of deep dive into the quiet infrastructure decisions shaping the future of global technology, now would be a great time to hit like and subscribe, because we cover stories like this the moment they happen, long before they reach the mainstream news cycle. Now here is where the strategic stakes become genuinely enormous, because this breakthrough did not happen in isolation, and it landed at an extraordinary moment for the company responsible for it. Just this week, alongside the Nature publication, news broke that IBM is finalizing a deal to acquire HRL Laboratories from its longtime owners, Boeing and General Motors. IBM has spent years building its own quantum computing strategy, primarily around a completely different physical approach called superconducting qubits. By absorbing HRL's silicon-based architecture and cryogenic control expertise, IBM effectively gives itself a second, parallel path toward large-scale quantum computing, rather than betting its entire company on a single technological bet, an insurance policy of sorts, against the very real possibility that either approach alone might ultimately fail to scale the way its own engineers currently hope. There's also a broader government dimension layered on top of this single acquisition. Earlier this year, the American government announced plans to award roughly $1 billion to IBM, specifically to help establish a new quantum chip manufacturing foundry in New York, a facility intended to serve both IBM's own internal quantum computing efforts and outside customers. Reporting on the HRL acquisition suggests the lab's chip production is expected to eventually shift over to that exact same New York facility, consolidating research, hardware, and manufacturing capacity under one roof, rather than spreading them across separate companies and separate coasts. In other words, within the span of a single week, a scientific breakthrough, a major corporate acquisition, and a billion-dollar domestic manufacturing facility all converged around the exact same underlying technology. To understand why the United States government is willing to commit this level of coordinated financial firepower toward a single quantum architecture, it genuinely helps to look at the much larger, much longer running technology conflict. This story sits inside the ongoing semiconductor and artificial intelligence competition between the United States and China. Since October of 2022, the United States has progressively tightened export controls, specifically restricting China's access to advanced chip-making equipment, cutting edge semiconductor designs, and the specialized software tools needed to design next-generation chips. The stated strategic goals behind those original controls were explicit: impair Chinese capabilities in artificial intelligence and supercomputing by cutting off access to the highest-end chips, prevent China from designing its own advanced chips by blocking access to Western design tools, and prevent China from building its own advanced manufacturing equipment by cutting off access to the Western components those tools depend on. Those controls have been tightened repeatedly since then, expanding again in October of 2023 and December of 2024, and expanding once more in early 2026 with new rules specifically covering quantum computing, components alongside traditional semiconductor and artificial intelligence hardware, introducing stringent new processing power thresholds and shifting licensing decisions for the most advanced. This policy fight has been genuinely contentious even within the American government itself. Congressional hawks have pushed for even stricter enforcement, with legislation introduced earlier this year that would grant Congress direct veto power over advanced chip export licenses, authority that currently sits with the Department of Commerce, while lawmakers focused specifically on China policy have written repeated letters opposing the export of certain advanced chips and calling for tighter restrictions on China's access to advanced semiconductor manufacturing equipment altogether. At the same time, the actual enforcement posture around these controls has shifted noticeably over the past year, moving away from loud public escalation toward quieter, more surgical enforcement, reflecting a genuinely difficult balancing act between limiting China's military and intelligence capabilities and preserving lucrative commercial relationships between American chip companies and Chinese customers. China, for its part, has not simply accepted those restrictions passively. Beijing has responded with its own escalating export restrictions on rare earth minerals and critical processing capabilities, where China holds a near monopoly position, essentially weaponizing its own chokehold over materials the rest of the world's technology industry depends on. China has also poured enormous domestic subsidies into building out its own semiconductor manufacturing capability, specifically to reduce its dependence on Western equipment and designs, with its domestic champion foundry repeatedly signaling progress toward more advanced manufacturing processes, even as independent analysts note the company has faced real delays getting there. Industry analysts tracking this dynamic closely note that despite years of these export restrictions, China's domestic semiconductor equipment imports have continued growing every single year, and Chinese chipmakers have continued making steady, if uneven, progress on more advanced manufacturing processes, even while remaining measurably behind the most cutting-edge American and allied manufacturing capability, with some estimates suggesting China currently produces advanced chips at only a small, single-digit percentage of American production capacity, a gap that some analysts believe is holding roughly steady or even widening slightly rather than closing. It is worth being candid that experts genuinely disagree about how effective these export controls have actually been at slowing China down, and that disagreement itself is worth understanding rather than glossing over. Some policy analysts have argued that export restrictions alone cannot substitute for a genuinely comprehensive domestic industrial and research strategy, and that Chinese restrictions have, if anything, pushed Beijing to double down even harder on its own heavily subsidized domestic development efforts, accelerating exactly the kind of self-sufficiency the controls were originally meant to prevent. Others argue the controls have meaningfully slowed China's access to the most cutting-edge manufacturing equipment and design tools, buying the United States and its allies critical additional years of lead time in the most strategically sensitive corners of chip technology. Whichever interpretation proves more accurate over the coming years, the underlying strategic logic remains consistent across both sides of that debate. Advanced semiconductors, artificial intelligence, and quantum computing are now treated by policymakers as a single, deeply interconnected, strategic battlefield, rather than three separate, unrelated technology races. This entire semiconductor and artificial intelligence conflict provides the essential backdrop for understanding why a single quantum chip breakthrough out of a small California lab is being treated as such a significant strategic event, rather than simply an interesting scientific curiosity confined to academic journals. Quantum computing sits squarely within the same broader category of technology that both the United States and China have explicitly identified as critical to future economic competitiveness and national security, alongside advanced semiconductors and artificial intelligence itself. American outbound investment restrictions, specifically, name quantum information technology, alongside artificial intelligence and semiconductors, as one of the three critical sectors where investment into countries designated as strategic competitors, principally China, faces active government restriction. That is not an accident. Quantum computing, semiconductors, and artificial intelligence are increasingly viewed by policymakers on both sides of the Pacific not as three separate technology races, but as three deeply interconnected fronts of the exact same broader competition for future technological and economic dominance. China's own quantum computing program has pursued an entirely different, and in many ways more publicly dramatic, strategic path than the quieter, more methodical approach favored across much of the American effort. Research teams centered around the University of Science and Technology of China have produced a string of headline-grabbing milestones over the past several years, including specialized photonic quantum processors capable of completing narrow mathematical sampling tasks dramatically faster than any classical supercomputer on Earth could manage. Just this past May, that same research group published results describing a machine reportedly capable of manipulating and detecting quantum states across more than 3,000 individual photons simultaneously, completing a specialized calculation in mere microseconds that researchers estimated would take the world's fastest classical supercomputer a length of time longer than the entire current age of the universe using traditional methods. That is a genuinely remarkable result from a pure physics standpoint, and it represents real, serious scientific progress that deserves to be taken seriously rather than dismissed. China has also built out a growing commercial quantum computing ecosystem well beyond just these headline physics demonstrations, with spin-out companies from that same research ecosystem selling quantum computing systems commercially, operating dedicated quantum communication networks described as the largest in the world, and releasing domestically developed quantum computer operating systems for free public download, explicitly intended to lower technical barriers for Chinese developers and accelerate the broader domestic quantum computing ecosystem. China has explicitly identified quantum technology as one of several strategic future industries to prioritize under its current national economic planning, placing it alongside advanced energy systems, embodied artificial intelligence, and next-generation wireless networks as pillars of its long-term technological strategy. But there is a meaningful and increasingly important distinction between generating spectacular headline results on narrow, specialized physics demonstrations and building the kind of complete, manufacturable, general-purpose control architecture that HRL just demonstrated. The specific machine that produced China's most celebrated recent result is what scientists call a specialized sampler, built specifically and exclusively to solve one narrow mathematical problem exceptionally well, rather than a flexible, general-purpose, programmable quantum computer capable of running the wide variety of different algorithms that would actually make quantum computing commercially and strategically valuable across many different applications. Experts examining these results have been careful to point out that this distinction genuinely matters, because completing one narrow specialized task at mind-bending speed is scientifically impressive, but it is simply not directly comparable to the kind of broadly useful, manufacturable, programmable quantum computer that companies like HRL and IBM and the American government backing them are actually trying to build for genuine industrial and national security applications. Publicly available Chinese patent filings and published research in this exact narrow corner of cryogenic control electronics, the unglamorous engineering problem HRL just solved, appear to be concentrated more around foundational device characterization and scientific instrumentation. Readout circuits, rather than a complete, deployed autonomously operating system already, integrated with a working qubit array performing genuine error correction. In other words, China has been racing hard and generating enormous public attention on qubit performance and specialized quantum demonstrations, while a quieter, considerably less glamorous engineering race over how to actually control and manufacture those qubits reliably at scale has, at least in this specific instance, been won somewhere else entirely, largely outside the kind of press coverage that China's more dramatic physics demonstrations tend to attract internationally. That distinction matters enormously for how this entire competition is likely to actually play out over the coming decade. Spectacular. Scientific demonstrations generate excellent headlines and legitimate national pride, but they do not, by themselves, create a scalable industry. Manufacturing compatibility, the ability to build a technology reliably, repeatedly, and affordably, using processes an existing commercial factory already knows how to run, has historically been the deciding factor in which technologies actually end up dominating an industry over the long run, rather than simply which technology looked most impressive in an early laboratory demonstration. That exact same pattern played out decades ago in the early history of classical computing itself, when commercially manufacturable microprocessors ultimately displaced far more exotic, harder to mass, produce alternatives that had once looked scientifically superior on paper. It is worth sitting with that historical parallel for a moment longer, because it genuinely illuminates why this week's news matters so much more than its technical details alone might suggest. The earliest computers were enormous, room-filling machines requiring teams of specialized technicians constantly monitoring vacuum tubes and manually feeding in instructions. Computing only became a genuine mass-market technology, and only became the foundation of enormous American economic and strategic advantage throughout the late 20th century, once engineers figured out how to shrink all of that complexity down into a single, reliable, mass, manufacturable microprocessor. The country and the companies that solved that manufacturing challenge first did not necessarily have the single most scientifically exotic laboratory prototype at any given moment. They had the most reliable path toward a production line. Quantum computing today looks a lot like those early room-filling computers, delicate, heavily dependent on constant expert supervision, and nowhere close to something you could simply plug in and use. Whichever nation solves quantum computing's version of that same manufacturing transition first stands to gain something similar to the enormous, decades-long strategic and economic advantage the United States built for itself the first time around with classical computing. Semiconductors themselves offer an even more direct parallel, because the exact same underlying dynamic is currently playing out in real time across that industry as well. American companies retain a substantial lead in chip design and certain specialized manufacturing equipment, but the single most advanced chips in the world are notably no longer manufactured primarily by American-based companies. They are manufactured overwhelmingly by allied partners overseas. That reality has troubling implications not just for classical computing and artificial intelligence, but explicitly for quantum computing as well. And it is exactly why American policymakers have grown increasingly focused not just on restricting China's access to advanced technology, but on actively rebuilding domestic American manufacturing capability across all three of these interconnected strategic sectors. Simultaneously, semiconductors, artificial intelligence hardware, and now quantum computing infrastructure as well. It is worth being genuinely honest about the limits of what this single breakthrough actually proves, because overstating its significance would be its own kind of mistake. 18 qubits remains a very small number compared to the thousands or millions of qubits that would eventually be required for the truly world-changing applications people talk about, breaking modern encryption or simulating pharmaceutical molecules with full chemical accuracy. This result is a milestone specifically in control architecture and manufacturability, not a finished, world-beating quantum computer ready to ship tomorrow, and it absolutely does not mean the United States has permanently locked in victory across this entire broader technology competition. China retains enormous financial resources, a rapidly growing domestic semiconductor industry, and a demonstrate term investment into exactly the kind of foundational engineering work that eventually produces breakthroughs like this one. Turning HRL's proof of concept into a machine with thousands or millions of reliable, manufacturable qubits will still take years of additional engineering, and there is no guarantee China could not still close this specific gap, or even leapfrog past it entirely, with a future breakthrough of its own. It is also worth remembering that HRL and its silicon spin architecture are far from the only serious American bet in this race. Other domestic companies pursuing entirely different physical approaches, including trapped ion systems, neutral atom architectures, and various flavors of superconducting qubit design, continue receiving substantial independent government funding and validation through separate defense research programs specifically designed to avoid concentrating the entire national strategy around any single technical bet. American policymakers have been explicit that this deliberately diversified approach, funding, multiple competing architectures in parallel rather than picking one early winner and abandoning the rest, reflects genuine uncertainty about which specific physical approach will ultimately scale successfully, and a recognition that placing every available resource behind a single technology carries its own serious strategic risk if that particular bet fails to pan out the way its backers currently hope. Still, it is genuinely difficult to overstate how significant the timing and coordination of this week's announcement actually is when you step back and look at the full picture. A major scientific breakthrough, published in one of the most rigorously peer-reviewed journals in the world. A major corporate acquisition, absorbing that exact breakthrough technology into one of the largest and most established names in the entire computing industry. And a newly funded billion-dollar domestic manufacturing facility, specifically built to produce this next generation of quantum hardware at scale, all converging within the span of a single week. That level of coordination between scientific achievement, corporate consolidation, and government industrial policy does not happen by accident. And it strongly suggests that American policymakers and corporate strategists view this specific chip and the manufacturable architecture underlying it as a genuinely critical piece of the broader technology competition currently unfolding between Washington and Beijing. Consider what actually happens if this specific architecture does successfully scale over the coming years the way HRL and IBM both clearly believe it can, and take a moment to picture the full downstream chain of consequences rather than just the immediate technical milestone itself. A country that controls the manufacturing backbone of practical quantum computing would gain the ability to simulate complex molecules for pharmaceutical research at a pace no competitor relying on classical computing alone could match, potentially compressing drug discovery timelines that currently take a decade or more down into a fraction of that time, delivering new treatments to patients years earlier than a purely classical approach ever could. It would gain the ability to optimize enormously complex logistics, energy grid, and financial systems in ways that translate directly into economic efficiency gains across entire industries simultaneously. And in the more sobering scenario nobody particularly wants to discuss openly, it would eventually gain the capability to potentially decrypt communications and financial systems currently considered secure, a capability with obvious and serious implications for both economic competitiveness and military intelligence advantage. If you have made it this far and you are finding this kind of deep strategic analysis genuinely useful, that is exactly the sort of content this channel is built around. So go ahead and hit that subscribe button now before we get into the final part of this story, because we will be tracking exactly how this competition unfolds in the months ahead. It is worth pausing here to appreciate just how directly artificial intelligence, the other dominant technology story of this entire decade, connects back to the same underlying quantum computing competition. Many of the largest classical computing investments currently being made by both American and Chinese technology companies are explicitly aimed at training and running increasingly large artificial intelligence models, and several leading researchers in the field believe that sufficiently advanced quantum computers will eventually accelerate certain categories of artificial intelligence training and optimization. Tasks that remain stubbornly difficult for even the largest classical supercomputers available today. That means whichever nation ultimately controls the manufacturing backbone of practical quantum computing may not simply gain an advantage in quantum computing narrowly defined, it may gain a meaningful compounding advantage in the broader artificial intelligence race as well. Further reinforcing why policymakers increasingly treat semiconductors, artificial intelligence, and quantum computing as three tightly interconnected fronts of one single overarching technological competition, rather than three separate, unrelated stories. That is precisely why a single chip, however small and however unglamorous the underlying engineering problem it solved, might sound to someone outside the specific field, can genuinely carry this much strategic weight. Technology competitions of this scale are rarely decided by any single dramatic headline moment. They are decided, gradually and often quietly, by which country first solves the unglamorous foundational engineering problems that determine whether an entire technology can actually be manufactured reliably at the massive scale required for genuine, world-altering utility. Export controls, outbound investment restrictions, and billion-dollar domestic manufacturing subsidies are all, in their own way, attempts by the American government to make sure it is the one solving those foundational problems first. And this week's convergence of a Nature publication, a corporate acquisition, and a new government-funded factory suggests officials believe, at least in this specific narrow but critically important corner of quantum computing, that strategy is currently working. Before you go, if you want to keep following the quiet, high-stakes engineering decisions that will ultimately determine which nation controls the technology that shapes the next several decades, decisions most people will not fully appreciate the significance of for years to come, make sure you hit like and subscribe so you do not miss the next story in this unfolding competition. There is a broader lesson worth carrying with you well beyond just this single chip or this single week's news cycle. Technology. Competitions of this magnitude are rarely won through any single dramatic headline moment, no matter how impressive that moment might look in isolation. They are won, gradually and often quietly, by whichever nation first solves the unglamorous foundational engineering problems standing between an impressive laboratory demonstration and a genuinely manufacturable, scalable industry. Export controls, outbound investment restrictions, and billion-dollar domestic manufacturing subsidies are all, in their own way, attempts by the American government to make sure it is the one solving those foundational problems first, across semiconductors, artificial intelligence, and now quantum computing simultaneously. A tiny silicon chip built in a research lab most people had never heard of a week ago just became one of the most strategically significant pieces of hardware in the entire ongoing competition between the world's two largest economies. Whether it ultimately tips the balance of that competition permanently in America's favor remains a genuinely open question that only years of additional engineering, investment, and geopolitical maneuvering will eventually answer. But this week, for the first time, we got an unmistakable dollar-backed signal about exactly how seriously the United States government and its largest technology companies are taking that question, and exactly how much they are willing to spend to make sure the answer comes out in their favor.